This conference will now be recorded.
Hello, good afternoon, participants. This session will be conducted by Professor S.R. Mohanty. He did his PhD from IIT Kharagpur. He's an associate professor with Department of Electrical Engineering, IIT BHU. He was a postdoctoral fellow with University of Beira Interior, Portugal. His research interests include digital signal processing applications in power system relaying and power quality, pattern recognition applications to DG-based systems, and also digital signal processing applications in power system relaying and power quality. Now, I would request Professor Sir to uh, deliver his lecture. Thank you, sir.
Thank you, Dr. Sanjay. Thank you. I am being privileged to get the opportunity to have one expert lecture based on the work being carried out. Anyway, just as I have worked in a diversified field, just as far as the optimization is concerned in the application of the power network, I thought that let some application, some practical application, how in an integrated power network it is applied and what is the practical aspect of the same rather than confining in the theoretical domain. So in that context, rather emphasizing on the various optimization techniques and its convergence, its feasible solutions. Instead of that, I will straightway go for the application in the power network, which will be immensely helpful who are working in this area, and future work can be carried out. So first of all, I will just go highlight the broad area, because in the power network itself, this title itself, the domain is very broad. If you see, so there are the various applications in the different segregated components art is its concerned, and the application is also based on the particular case and domain specific, and a lot of consideration, lot of constraint being taken into the consideration. So in that scenario, so a wide area large scale network will be first discussed, followed by the microgrid aspects and different protection aspect where the optimization is explored. So first of all, let us understand how the optimization now, how it plays an important and crucial role in an integrated power network. And the power network infrastructure, all of you know, and its inherent characteristics subjected to any excursion, also you are being familiar with. But the more emphasis is that there are a lot of nonlinearities, different saturations, dead bands, and different on contrary to the classical power network, in the converter dominated and a lot of power electronics converter dominated network, and your SVDC, your FACTS, your different type of loads, and its inertia response. It is very difficult, it is very complicated on part of you to realize unless the specific approach is being adopted to get the expected response for the same. And so what was initially the classical power network, the infrastructure was not complex, but the augmentation nowadays with the renewable penetration and with the communication infrastructure also being dominated, your total approach for the power network for a particular decisive action to be made, whether it is in a control domain, whether it is in a protection domain, whether you are in a planning, you are going for the power system planning, there you have to have a rigorous and a comprehensive analysis for the same. Because when your power network, you suppose you take a integrated power network operating in a particular operating point and subject it to the excursion, the post-disturbance equilibrium needs to be visualized. And subjected to that, how the rest of the component is expected to behave, that is also a point of that is a major challenge, and how you are addressing the same. So it is a very broad area. I'm not going in details in that area. So people thought, so how this PMU based wide area monitoring, uh, the classical power network, the control philosophy, and other your optimization based, basically it was dominated by the local information. But with the incorporation of the phasor measurement unit, thanks to Professor A.G. Fadke, who was have a tremendous contribution for the augmentation of the power network infrastructure. Just you see the signal processing, the lot of control effort, the optimization. It was already the mature technology as far as the power system network infrastructure is concerned, and you have the corrective action accordingly is being made. But it was not adequate enough with respect to the increased penetration of the renewables, different power electronics converter based sources, the power electronics converters being penetrated at your part of particular point of common coupling, different type of generators, so starting from wind turbine generator type 2, type 3, type 1, and you have the solar in the transmission level, and the distribution level you have the MPPT boost converters, and lot of power electronics based analysis is also prevailing for the same. So when the wide area information is coming for a decisive action, try to understand. So because we are always talking about the techniques, the comparative analysis, and in the research paper it is being focused without understanding the base. But the important aspect is that apart from the local information, when you are taking the global information, now is it really possible? Because suppose you have a IEEE 39 bus system, so you have a benchmark system, benchmark model, and sometimes you have taken the model according to your own convenience based on a particular infrastructure being considered. So for that, if the latency of the your packet, whatever the with respect to the certain communication infrastructure according to the communication protocol, if it is being transferred from one end to the another remote end, so from the remote end to the end where you are taking a decisive action, in that context, if that is not tolerable for a expected decisive action that has to be made for the subsequent remedial measure to be initiated, it is not tolerable. So in that context, Fadke, he thought, okay, let the visibility of the grid be made. That means some states are measurable, some states are redundant, some states are also obtained by some estimation techniques, and this information, this all the information, whatever it is coming, whether it is from the local end or to the incorporation from the SCADA, from the again with the hybrid, that means the SCADA, PMU both. So that means at the control center, in order to make a particular decisive action, we have a adequate data. So for that, so initially, for instance, the power system stabilizer, because all of you know that with the respect to the your particular your rotor oscillations, that means data that is subsequently impacting the rest of the power network. So this your inter-area oscillation, intra-area oscillations, this has to be diminished with respect to the available signal, with respect to the signal information being available. So for that, whether in addition to the local information, if the global information you are taking into the consideration, what is the possible objective function in order to be initiated for the same, to have a control effort for the to go to get the your to diminish the oscillations in the rotor. Similarly, Now, as I told you, the communication infrastructure, when it is apart from the power network being dominated by the renewables and with the augmentation of the lot of power electronics converters, the communication infrastructure also plays a crucial role, because the PMU, for instance, the IEEE 37.1138 and the different intelligent electronic devices, that is IC 61850, the communication protocols, and you have the sample value undergoes meshes. So that means you have the rigorous analysis of the communication infrastructure. Apart from that, the congestion, routing, priority of the message transfer, all has to be taken into the consideration. And now the issue is that you have taken a case of 2012 blackout, analogously the Ukraine blackout also. So in that distribution grid, so the cyber attack, that means you have to make not only the power network the robust, intelligent, it should be also resilient. That means we have the integrated power network infrastructure has to be cyber resilient. That means with respect to the attack at a strategic location, the this whatever your remedial, whatever the decisive action you are making, okay, up to this severity of the attack, the total decisive action is not going to get affected for the same. So that now the question is that you have in a different time frame, your power network has a different time scale, and the segregated time frame is also different, starting from the mechanical transient, electromechanical transient, and the electrical transient is the time scale separation that you are talking about, and the cyber based, that is the event based. So now how to get the total the impact analysis if you go for that? So you have to ensure whether it is being manifested by the attack or it is generated by the for all the that is from the sensor failure or any fault or any initiated that in the integrated network any fault, any disturbance is there. That means this classifier has to be intelligent enough to go for a sufficient margin for the same. So there you have to go for the optimization. You have to go for the selection of the slack variable. You have to go for the Euclidean surface and overlapping of between the two identical classes. There you have to distinctly go for that. And similarly, the load frequency control, it is a well documented in literature. Load frequency control, so I am not going into details for the total primary, secondary, and the tertiary control and all aspect about that. But however, with respect to the intermittency and the stochasticity of the source being connected, there the robust control is a strong candidate, because you have the exogenous output, you have the disturbance rejection, and you have the stability margin, robust stability margin, because you have the solar insolation temperature, it is not within your hand. The wind speed subjected to a particular your topological region, that is not within your hand. So subjected to the stochasticity and the intermittency of the prevailing source that is being connected. So for that, what is the expected? Because you have to go for this, your frequency profile has to it has to be maintained in the steady state after a tolerable time that you are taking into the consideration. Similarly, okay, in the transmission network, as you talk about, in the distribution network also equally, and the microgrids, there also you have the importance of the optimization. That means you have the lot of states being in guard. Apart from the total, you have the average model, you have the phasor model, you have the transfer function based model, you have lot of states being available, and your equation being aggravated to a higher order. So when you go for the reduced order modeling without sacrificing the original behavior of the system, you have to discriminate between the slow state and the fast states, and accordingly the optimization function has to be formulated so that you are preserving the original original feature of the system, and correspondingly you are going to analyze, you are going to reject the disturbance, you are going to achieve the robust stability margin, you are going to have the error minimization simultaneously in a weighted combination, and you are going for the reformulation of the objective function based on the norm bound, because it is inherently a exploration of the robust control. And this is so I am very quickly I'm telling. So the PMU, as I told you, so that means you are getting the synchronized measurement from the all. You see the power network inherently, when you start from the generator, the classical model, when you take this, when if you are taking the silency, if you are taking the if you are modeling the primitive model of the generator and the time varying form of the inductance, and correspondingly you are formulating the differential equation for the same, and taking all the things into the account, this equation being manifested to the aggregated from the generator transformer frequency sensitive model of the transmission system and other your frequency sensitive loads also. So all in cascade has a higher order differential equation. Exactly, you cannot get the solution, that means as a explicit function of time. So for that, so when you are, so that means that is again another domain, as I told you yeah, just in the past slide, that that domain I am not discussing here. But my focus is that you have to deploy the PMU. Now the question is that PMU, is the cost okay? The communication infrastructure cost has tremendously decreased. That is fine. And you have to obtain the phasor measurement. That means you are obtaining the phasors. That means the inherent, for instance, the DFT block is there. You are getting the fundamental phasor which is taking a relevant information for a decisive action. But the question is that you have a large scale network. Are you going to deploy the PMU at all locations? Remember, whenever you are talking about a technology, you should talk about the cost. It is not that the cost, whatever the technology that you are trying to implement or develop, it should not be confined within a theoretical domain. The practical feasibility should be associated with the cost, because the you are suppose in India now you have let us tell that you have already the 1700 or 1800 PMU, or and you are going to go for the visualization of the northern grid. So in that scenario, so you have lot of you have SBTC, you have multi-terminal DC from the your northeast to Agra, and you have you have multi-terminal DC, you have SBTC, you have the different other your renewable energy resources being penetrated. The question is that the when you are extracting the phasors in a synchronized manner at a strategic location, okay, you are getting the phasor information, that is fine. You are getting the huge amount of data for the subsequent analysis. That means you are giving a data driven analysis you can have for a control aspect, for a protection aspect, for a planning aspect. That is fine. But the issue is that, are you going to deploy the PMU at all nodes? No. So for that, let us you have to optimally place the PMU in a strategic location in a such a way that it has to that means the system is your complete observability of the grid is there. That means complete observability. Why it is required? Apart from the local states being available, if some remote and the states is taking a relevant participation for a decisive action to be made, you cannot take that state as redundant state. Try to understand. So the minimum number of PMU required for preserving the complete observability and the maximization of the measurement redundancy. That means you are taking, and sometimes when you are taking a objective function, remember, when you are taking a function, that function is nonlinear, and if it is a straightforward
you cannot directly get the point of inflection, or you are not getting a feasible solution in a particular space. So there, if your feasible solution in that particular space, when you are considering that into the you are considering that into the account, so you have sometimes the conflicting scenario. The conflicting scenario subjected to the constraint, it is again another further aggravates the problem, because you are taking one objective function. Okay, this loss minimization has to be it has to be achieved. For instance, this PMU placement, that means your system has to observe, it should be completely observable, and you have to maximize the redundancy. That means some measurement which is not relevant at all. That means this has to, so this maximization of the redundancy will have a frame decision of the decisive action that has to be made. So for that, again, the optimal power flow. uh, Remember, optimal power flow. What do you know? That means you are taking the power flow in an optimized manner, and because you have all, now you have a lot of as I told you, you have the SBTC converter, you have the rectifier end, you have the inverter ends, you have the firing angles, alpha minimum, alpha maximum. Correspondingly, the coupled power flow you are computing. So when you are designing a Pareto surface and you are propagating the error in that, so corresponding to that, now you are talking about the minimization. Okay, is it the adequate objective function that you are taking into the consideration? Certainly not. Sometimes the environmental adaptive factor is also, it has to be uh, taken into the consideration in order to have a augmentation of the formulation of the objective function. So if that is taken into the consideration and two are contradictory to each other, I'm unable to get a feasible solution for the same. So for that, okay, you are going for the different optimization. People used to tell a lot of optimization technique, that is meta heuristic optimization and the environmental adaptive optimization. This technique it has a faster convergence, and it has, with respect to this iteration, this has the feasible solution is this, and these are the optimal value of the constant that you are getting. But certainly I would like to tell, is it really possible that you are telling this technique is better than that, and you are formulating certain mathematical formulation based on that, but it is ultimately the based on the one principle. You are going from the source to the destination in an optimal path. You have a higher degree of freedom, and your particle, they coordinate with each other, and and you have the local minima and the global minima. Sometimes it is trap trip the local minima. That stagnation of the parameter is being taken care of, and subsequently you are taking a parallel action also. That means the two objective, the stagnation of parameter of one formulation of the object, your optimization function and the technique being carried out is being taken care by other, and vice versa, and ultimately you are getting a feasible solution in the search space. And rest of the mathematics is just it, I'm not telling it is just this is just only, okay, one improvement is there. uh, it is this, the with comparison to PSO, your hybrid PSO, your GA, your differential evolution, your ABC, your BAT algorithm, your lot of algorithm that you talk about, and ultimately you are going for the integral time error, or ICE, or integral square error, whatever it may be. So you go for either minimization of a function or a maximization of a function. So for instance, here you are taking this measurement redundancy and the number of balls where your PMU is being deployed, and you are formulating the objective function in a such a way that you are visualizing the total visibility of the grid, and where you are obtaining the corresponding state for the corrective decision in context of the in context of the different segregated domain that you are talking about. And this is the mathematics, okay, by the time have your different hyperbole function, and these are the empirical update of the different, the Jaya itself, the victorious, it is even on contrary to the inertia weight and the different parameters C1 C2, and it is not in the gradient surface, it is not going in a differential manner. Differential manner, remember, when it is in the gradient surface, it aggravates if the noise factor is there. So the propagation, so it is a straightforward optimization technique, but it is okay. But I will not emphasize. I am not much familiar. Anyway, this is one optimization algorithm being incorporated for the optimal PMU placement. So now you are taking the PMU placement. You have focused on the optimal location. Okay. So that means the topological information of a particular network you have got. But is it really the case? So you have to take a lot of factors into the consideration. Lot of factors are what are the possible factors when you are exchanging the information from PMU to the PDC, phasor data concentrator, the communication infrastructure, the congestion in the communication, and the priority of the exchange of the information with the routing, if the communication failure is there. So correspondingly, again, there will be augmentation of the objective function in context of the communication constraint being taken into the consideration. So for that, so here when you are taking, so when you map, if you take suppose a decisive action is a function of the centralized control, and with respect to the decentralized control, that means ultimately the control action in the decentralized control, you are getting certain decisive action, and you are getting to the centralized action for the final decision to be made. Analogously, distributed optimization nowadays being applied in the power network. That means when you are taking a feasible solution, when you have to take the total optimization as a modular and independently realize the same with the cloud data and the exchange of the observation of the optimization in a particular subspace with a particular space, particular boundary where you are getting the expected feasible solution and exchanging the information among them. So there the communication infrastructure dominance plays an important role. And there also the optimization function has to be explored for the same in concatenation with the normal power network, your optimization function being formulated. And this is the with respect to the result that you are going with respect to the binary joy algorithm, and this taking into the consideration. So again, I will go to the wide area your power system oscillation. So this is also designed. So let me take this one. This is okay. So just you see here, your generator box, you have the PMU being deployed, and you have going, when you are going from the PMU to the PDC, that is the constant delay and the variable communication delay with respect to the communication infrastructure. You have the fiber optic cable and your other communication media that you take into the consideration. That means you see your PMU is there. If there is an inherent delay, that delay, when that means your local PSS is there where the wide area control signal is coming into the picture, and your AVR, your excitation system, that where you are getting the reference and your control signal for the local PSS augmented with the wide area PSS, that has to, your time delay for, has to be compensated for the same, and your wide area PSS has to be designed in this respect. So for that, so what is the inside block of this? Your gain block, it is just like an amplifier, and your lead lag compensator, which is for the attenuation and the phase shift, if it is there, that has to be taken into the consideration. And you have the saturation upper bound and lower bound respectively. That means you are getting the expected control effort, control signal, that you are augmenting the local signal. So you are getting the rotor speed in proportional to this in context of this wide area PSS design, and you are ultimately achieving in your your reference voltage is there, and this is your terminal bus voltage, and you are getting the error which is going to AVR with the excitation system. So now issue is that when you are formulating the objective function, you have the lot of constraint. You see the intermediate blocks. So if you have the lower limit and upper limit respectively, you have the sometimes this inequality constraint may not have a feasible solution. Just you see your very simple example I am talking about. If you remember the normal economic load espace, you have formulated the Lagrangian function in lambda, the iteration, this function of the penalty factor, and correspondingly you have you have taken a heuristic choice of the lambda, and you have taken a equality constraint optimization for the economic load dispatch. So in this scenario also, the analogous phenomena, sometimes the inequality constraint with the upper bound and the lower bound may be relaxed in the lower bound, may be relaxed in the upper bound, but again the trade-off has to be very crucially, very technically, it has to be tackled. It is not that arbitrarily the lower limit and upper limit we can fix, and we can go beyond suppose your kc minimum and kc min, according to my choice I will take it, so that the feasible solution has to be maintained. It is not like that. So it has to be tackled in a such a such a technical manner that the upper bound and the lower bound, some relaxation will not affect the feasible solution in the search space. Try to understand. So that is the all the basic, because unless we understand this, only going for the mathematics, okay, we should be, as a background of the electrical engineering, we should be very strong in mathematics, but at the same time, unless the physical interpretation and its practical implementation is not realized, it is meaningless. So for that, so when you go for the time delay compensator, sometimes it is event based. That means you have to go for the event based triggering for the delay that has occurred, because it is a that is from the remote end, and from the PMU to PDC, that is a considerable delay is coming into the picture. Unless you compensate the delay, your control signal being taken as a augmentation has not a corrective decision for a local PSS design that you have made so far. So so this you have taken this time delayed signal, and correspondingly this compensation based on the event triggering. Remember, now the control effort in a multi-agent sense, in a different sparse your communication, all you are taking in the event based reduces the control effort, the computational unnecessarily, the sensor burden has been tremendously reduced. Okay, at this time the actuator or the sensor has to be initiated, because this is okay, it has it went beyond the reference, so this initiation action has to be done, and at that time you have to ensure our communication infrastructure is reliable. Only that is the limitation. So that the event based triggering, it is a very a very elegant choice. The event based triggering will have the corresponding decisive action for any control effort that you are taking into the consideration, right? So for that you have the corresponding, you have the eigenvalue analysis. Okay, that is, this is straightforward. You go for a state space matrix, you formulate your a minus lambda I, correspondingly the participation factor, and say eigenvalue sensitivity and the dominance of that you evaluate. That is okay, and the system the stress condition, and you correspondingly you design your PSS when there is no PSS is there, when the local PSS and the local PSS augmented with the wide area PSS. So this again, as I told you, the cyber attack resilient, because the attack vector, when it will go, when it is, whether it is a false data injection, whether it is a ramp attack, it is a coordinated attack. So correspondingly, if you have a secured message transfer, as far as the wide area PSS design is concerned, that means whatever message is being transferred from the PMU to PDC, I have to ensure, okay, this message is encrypted. That means whatever the message, the PMU local, so PMU, suppose you have a lot of PMU being deployed, which is going to the PDC. So correspondingly, this cryptography, this message security will have the, in analogous to the your objective function being formulated, your secured message transfer also plays a crucial role. If your communication infrastructure may be reliable, that is fine, but suppose your PMU1, when it is transferring the message, because the PDC has to take an action for the corresponding visibility of the grid in relevant to PMU1. So if at that instant I am getting the information of PMU2 due to some hack action, so that the PMU2 information will have a corresponding effect on the PMU1 and vice versa. Vice versa may be there, may not be there. We cannot ensure about the same. It is completely unpredictable. So for that, what will happen? So ultimately, so that means you have the corresponding, it is indispensable on part of you to get the information of the PMU1. So for that, so you have to make it is the that means the cryptography, that means it has to, the message has to be secured. That means, okay, at this instant the decisive action whatever I am getting, I am exclusively getting the information of the PMU1 to get a corresponding decision to be made at the PDC, phasor data concentrator, right? So for the cryptography, so this is just this, you see, you have the MAC generation, you have the time delay, packet drop, cyber attack, this is the malicious data injection, and correspondingly you are getting the time delay. You see, time delay compensation, I told you time delay compensation. So first of all you have to model a delay. Now the delay model you have to so you know, all of you, the transportation delay, your expansion of that with the Taylor series, if you go for the about a nominal operating point 1 minus ts plus ts square by 2 factorial and so on, right? So the time delay exclusively, how I have to model a fixed delay as well as the variable delay. So sometimes this modeling, this compensation, there also we have to go for the optimization. And remember, people tell, okay, the optimization feasible solution, whatever you get sometimes, and we have the available fast processor for a decisive action. But now the question is that, is the optimization has to be done at that instant in a parallel manner, or in an offline basis? You are taking the parameter already in a predefined way and you are just fitting that for a decisive action. That you have to make subjected to the action to be made at that instant, whether it is crucial or not. Otherwise, in a steady state scenario, you can take some action and which may be relevant for a successive decision to be made. For instance, the planning, you are going for a very your higher time scale, your some sluggish time scale is it is expected. So you are going for a time series model from your ARMA, your autoregressive moving average, your ARIMA. So that means you are best fitting your price data in form of a time series model. So when you are best fitting that, that means what you are exactly, when you are going for a forecasting, so that means you are going for a planning for another 5 years or 10 years. So that means when you are, so once you are fitting all the coefficients in a least square sense, evaluating the pseudo inverse, or you are getting any augmentation in artificial intelligence technique, you are evaluating the different coefficients in an optimized manner. So this is going to help you in a planning. So that means what is exactly happening? So you are retrieving this and you are fitting into the time series model, you are optimizing the same and you are going for a planning, but which is at a higher time scale. Okay, so the planning action, but when you are at a faster time scale, The decisive action is very crucial. You cannot tolerate that. Any mistake, any the control effort, remember the control effort event based, the faster transient associated. For instance, you are modeling the generator. You are modeling a generator subjected to the faster transient. So they were direct axis and corresponding time constant. It is coming into the picture. At the same time, the mechanical the associated transient associated with the mechanical time constant is no more coming into the picture at that time. So when you are taking, so now you are, that depends upon the priority that you are going to take into the consideration for the same. So for that, so I have to get it adequate time delay. So time delay subjected to the model infrastructure. Have I the adequate knowledge about the model and what is the possible states? What are the, when you are linearizing about the operating point, when you are linearizing that, sacrificing all the higher order terms, whether it is really sacrificing the model accuracy for the expected response to get achieved, whether we are going for that or not. That decision you have to make accordingly. So the again, the objective function has to be formulated and the constraint has to be taken. The conflicting scenario is also taken into the consideration in the surface where you are designing for a feasible solution to be made. So this is again your participation of with respect to different modes and corresponding factors. So I'm going very fast because we have a lot of things. So also this again the objective function when you are going to formulate. So in apart from the local your speed information rotor speed, you have the wide area and with respect to the particular time span when you take into the action, and then you go for the optimization in order to evaluate the constant by PSO, TLPO, hybrid optimization. Sometimes it is as far as the convergence, computational burden, and the total feasible solution to be made. So, for instance, your PSO, your C1, C2, inertia, weight, and correspondingly, how that plays an important crucial role. If the stagnation for the C1 and C2 is there, you have to make it time varying, and correspondingly, if so, how not only the faster convergence, the feasible solution. It is not only the people tell, okay, the faster convergence after this, the convergence by after 50 iteration. I am getting this curve. It is not the case. You are getting the curve, that is fine. But are you going to achieve the conflicting objective function criteria in a trade-off manner? You have taken a single objective and you have formulated a solution for the same. You have ignored other factors simultaneously. So that is not a correct decisive action. Try to understand. So the conflicting action in a trade-off way, taking the feasible solution to be made and designing of the surface, and in the domain, okay, the feasible solution that lies in that boundary in the nearest neighborhood, and it is not affecting the total integrated power network behavior subjected within any excursion. So my total your total objective it is going to get fulfilled for the same. So this is for the different parameters being obtained, your lead lag compensator, your gain, and your different correspondingly you are getting with respect to the wide area PSS design. And this is wind integrated. Again, the stochastic, this is stochastic. Try to understand what this is stochastic source. So the stochastic source, when you are being integrated, so inherent characteristics of that source has to be taken into the consideration for the population for the specific objective what you are going. If you are going for a load frequency control, whether you have to take the inertia, whether that means the synthetic inertia, the virtual inertia factor, and the inertia response when you have because your secondary control action has to be very fast. So are you taking into into the consideration? But now, okay, this is in the similar way, so I don't want to go in details in that. So I am skipping this. And this is all of you know this load frequency control also. So this also I am skipping. So this is I am telling this one. S infinity control using LMI approach. Suddenly I came to this how it is a discrete thing. Load frequency control all you are aware of. Your tie line, your predefined power exchange, from between the area 1 and area 2, and your generation load mismatch. These two criteria has to be fulfilled, and accordingly your control from the primary, secondary action has to be made, and for the tertiary you have the economic dose. This is okay. But now the question is that you have the power network itself have lot of sensors, you have the different actuators, you have the retrieving the signal of the different at a strategic location which have the different, you have the non-linearities, and you have the different dead bands. Lot of your in a segregated components there are a lot of features that as per our understanding. So that means your disturbance is manifested. So in when you are modeling something in focus of the signal, accordingly you have to also not ignore the focus of the noise. So the concatenation of the importance of the noise and the signal taking in a parallel way, that means the importance of the noise, unless the disturbance rejection is there, not there, unless you are achieving the robust stability margin. That means now my power network is already in a stress. You are already at the nose point. You are at the verge of instability region, almost, right? You are already at a stress limit. So the control efforts of the load frequency control or automatic generation control, whatever you are talking about, with respect to now the classical power network, it was straightforward. And people are tell why were the transfer function was faster? Anyone can tell why the transfer function was faster? Because the mechanical, the associated your all the mechanical time constant and other factors taking into the consideration, that doesn't play an important role as far as the load frequency control time scale dynamics, that you are standing at the particular time scale that you are taking into the consideration. So your faster model is adequate enough. You can now you can argue your actual replication of a segregated network really consists of a lot of incorporation. Why you are sacrificing that? That is a basic question. But the answer is that in the time scale where I am standing, these are the redundant informations. And correspondingly, now the question is that I have a inheritant. Now you have the type 2, support type 2 wind generator, type 3 wind generator, and you have the MPPT boost converter. You have the again oscillation of your maximum power point about the operating region. So these are all there. And you don't, and sometimes you don't have the control about the stochasticity of the system of the source being connected at a particular your point of coupling. So in that scenario, in that context, if you don't design the controller, if you don't design the controller in accordance to that, so your total objective get defeated for the same. So you are going for the stabilizability, detectability, non-observability and non-controllability of that, and you are getting this, your PS is the plant. Correspondingly to the exogenous, your that means your control law is that the effect of disturbance on the control variable is expressed in terms of the infinite norm. You have the second norm, your L1 norm, L2 norm, the Euclidean distance error function, and the E transpose E, your integral of that. When you go for the your error, you are taking in the gradient surface. So this is the augmented plant. You are taking a state feedback control if you normally you equal to minus of kx. So the exogenous input has to be also taken in concatenation in with respect to the plant infrastructure being taken into the consideration. So the objective function is that minimization of the gamma. This you see ACL is the augmented your A, that means the plant dynamics. Controller and plant dynamics co-catenated with each other. And this is the LMI. This is the linear matrix inequality in the feasibility region in the matrix that you go for the convex optimization that for the your total your feasible solution to get achieved for the same. Now the semi-definite matrix has to be this symmetric matrix has to be formulated subjected to this infinite norm. This has to be minimized so that the robust stability margin has to be achieved. So this is the transfer, this is the infinite norm of the transfer function from Z infinity to top low, which doesn't exceed the specified limit. This is the application of the objective function. You can't go to the plant. People will argue our PI control is adequate enough. What is the necessity of this Zeigarnik method? I will go for the heuristic of that. That is adequate. My industry is quite satisfied for the same. But practically it doesn't. We have to convince to the industry people. Okay, now the era has come. The robust control has to be implemented in a practical industry where you have the solar park, you have the wind, and a lot of your renewable penetration at a strategic location that you are talking about there, because you are talking about the cost. Your grid code compliance, remember your sometimes this Gujarat, they are now flailing with the grid code compliance for the wind total being generated. They are unable to connect to the grid in a very significant manner. They are the LVRT that compliance is not there, and lot of defects are there, lot of flaws. So subjected to that scenario, we have to go for the this stability margin. So remember you cannot just your grid infrastructure now you cannot tell it is a classical network. It is wrong to tell it is a classical network, but however you cannot dismantle the statcom at a strategic location for the reactive power support. It's already there. You will tell, okay, I am designing some new control technique, and this is the new reactive power support or this from the different manufacturer. I will dismantle. No, because India, we cannot pay for that. We are not a very developed country. So for that, we are not dismantling the existing equipments. Try to understand, we are not dismantling the existing equipments that you are talking about, but at the same time you are augmenting the technology without sacrificing the grid stability. You are augmenting the technology without sacrificing the grid stability. I would like to repeat it. So the different grid interactive parameter, as far as the control design is concerned, there the optimization plays an important role. show robust control concatenation with the optimization. It is not only the robust control, the optimal control, suboptimal control also. So people, when you take out the load frequency control, we always go for the transfer function fast order, and after that you go for the design of the same, and you go for the PSO, BAT algorithm, this harmony search and all, and we go for a comparative graph of that subjected to different scenario, IC, IT. This is not the way of, we should go, okay, something has been done, now we should relook into this type of research. This is not feasible in the industry as a practical application is concerned. Okay, so this is the mathematics concerned about this as far as the state feedback and all. So I am skipping it. And another important I would like to tell you just one thing. Okay, uh, let us okay, this small signal analysis, as I told you, in the microgrid now it is again another revolving that technology. You have the AC microgrid, DC microgrid, AC DC microgrid coupled with the interlink converters with the exchange of the power, and it is connected at a particular PCC. Again, the nanogrids are also there. DC nanogrid connected to the DC bus, AC nanogrids. So you have the power flow. You can go for the optimal power flow subjected to the different. Now you see different power electronics converters are there. The dominance of the power electronics converters and its state space modeling. For that, for instance, I am taking this into the consideration. This is this normal thing, you know, this current control, and remember the current control loop is always faster than the voltage control, and you know the transformation and switching poles corresponding to the voltage source that inverters, and this is your PCC, and you have the transformation of the same. Now, these are the two modes. One is your grid connected mode and autonomous mode. So when you go for the formulation of the state space, there are a lot of states being involved. Some states are faster states, some states are low, some states are faster states, some states are the slower states, and some states are the intermediate between the fast and slow. So when you linearize this linearization, all of you know what about the operating point, some small excursion, and this is the incremental state space that you take into the consideration. So for that, so now I'm going to one thing, just instead of this one, just you see here, error norm. That means you have formulated the objective function. This is the reduced order norm. That means you have gone for the either for the balanced truncation, your different reduced order modeling is there. So that means your transfer function as if your L1 norm, your S2 norm. That means this is the integral for the absolute error, and this is the system response to the white noise and represent the error, and this is the maximum gain of the error function in the frequency domain. So these are all factors. If the norm based, if you have the actual plant, that is GS, and this is the reduced order plant, that is the GRS, and this is the error function. So this is the fast norm, this is the second norm, and this is the infinite norm. So this co-catenated together, that means this is one objective function for a specific action to be made. This is for the another specific action to be made, and this is another specific action to be made. In a weighted manner, I have taken this formulated mixed norm objective function formulation. So when you are taking this mixed norm objective function formulation, you have to minimize the same. I told from the initial thing, that means you need not sacrifice the accuracy of the network. Correspondingly, you have achieved the reduced order model, but however, now you are ensuring whether my reduced order modeling is competent enough to take a decisive action. I have to reject the disturbance. I have to minimize the error. I have to go for the corresponding. So that means you have, this is in a weighted manner. You are taking into the consideration as a weighted manner. Then you go for any objective function, J algorithm, ABC algorithm, whatever you are. So ultimately, so this will go for the minimization, and correspondingly this is one aspect, and you have to correspondingly the gain margin, phase margin is for the your in your frequency domain, and correspondingly the stability as you have to get into the consideration. And another aspect I will tell you this yes, relay coordination. Remember, the classical network, simple overcurrent relay. Let us not talk about the distance relay and differential relay. That will also come into the picture. I will tell. Relay coordination. That means in the protection, this coordination plays an important role. Remember, the protection action has to be very, very crucial. Now you see, you have the bidirectional power flow with respect to the renewable penetration. So there are a lot of issues: sympathetic pre-tripping, blinding of protections, the zone boundary. These are a lot of implication with respect to the renewable penetration, and the converter-based dominance in the network has not a sequence component straightforward. If you resolve the normal, if you are taking an unbalanced system, you are taking the positive, negative, and zero sequence respectively, and correspondingly you are realizing the segregated network in a straightforward, and you are integrating the same for a particular objective. But when you are a converter dominant source, the exact modeling for the same is indispensable. The sequence component realization for the same is not straightforward. The short circuit contribution with respect to the renewable energy penetration and the corresponding modeling is not straightforward. The sequence component analysis in accordance with that is not also straightforward. So here you see, again I am telling this only one thing: objective function minimization is what? Relay operating time. So you have the boundary, what? Your TMS, your T minimum, T maximum, your coordination time interval, bound of the pickup current. But with respect to that now renewable penetration, this has to be relooked. So that means you have the fault at a strategic location, F1, F2, F3. You formulate this, you go for the linear combination of the same, you go for the objective function formulation of the same. Correspondingly, you evaluate the relative, your total relay operating time subjected to the total your bound that you are taking into the consideration, and accordingly the coordination time interval, your upper limit and lower limit, it is not going to get violated for the same. So this again it is with the PSO and gravitational source, and combined of that, this we have and hybridization of that for the TSM and PSM respectively, and with the grid connected mode and islanded mode. And this so this is all about so because in a glimpse that I discussed, why always we talk about just things very superficially. What what I exactly want to tell you, we should know the in-depth mathematics of something before we go for the technique. People used to go for, okay, then the MATLAB, some codes are available, and just go for modification of the same, extrapolate some curve and describe something and get some research. It is not going to help you in a long run. Are you getting a point? So for that, unless you have a proper understanding, when you are going for the modeling of something, what are the associated variables, what are the possible excursion, what is the expected response you are supposed to get subjected to any disturbance. You have to go for the in-depth analysis of that. And now you are taking an integrated power network. Power network itself, not only the complex, further amalgamation with the communication infrastructure, dominance of the power electronics based converters, renewable energy resources penetration, how it has to be relooked, and the formulation of the objective function for a different decisive action has to be made in accordance with that. So that from my end. So Sanjay, just so I think I have other assignment actually. So I have to. Is it okay?
Thank you very much, sir, for such an knowledgeable and enlightening lecture. I would request participants to ask if they have some query related to sir's presentation, or we can then end the session. So, any participants who wants to ask something to sir?
You can do one thing, Sanjay. You can also they can
Yes, sir.
send with the mail also if the queries are there.
Yeah, I'll share your email ID with all the participants. So in future also, if anybody wants to ask something to sir related to optimization or any other query, so he or she may contact sir. So thank you
In
very
not
much, sir.
only in the optimization, in the signal aspect also, try to understand.
Yes, yes.
Optimization is
Okay.
not only adequate, because we have to think in a very in-depth. Try to, again, I would like to tell you one thing. You should be very strong in mathematics if you are really going to do a good research. And
Yes, sir.
mathematics is not only a formulation of the mathematical things, has to be made in a practical sense.
Yes, sir. Okay, then I think, sir, we can end the session. Thank you very much, sir, for your precious time. So we can end the session, sir.
Okay, thank you.
Good day, sir. Okay, thank you very much, sir.